How's it going? My sound okay today?
Yep.
I was having some issues with it during office hours yesterday, so I'm glad it's okay. I got tired from previous classes. That's relatable. I've been at a conference this week. So there's a conference in earthquake physics that's usually in Palm Springs at this time of year every year. But because it's online, it's kind of set up differently. And so I'm teaching kind of in the break between sessions. So it's kind of a big jump to go from talking about earthquakes to talking about minerals. But here we are.
I have a quick question.
Yeah.
Monday's lecture slides about the beginning portion of minerals. Are you gonna post them on Canvas by any chance?
Yeah, they'll go up today.
Okay.
What I'll do is I'll put, because I make one big PowerPoint for each topic, it goes up after I finish with that topic. So I'll put this up right after class. Has everyone been able to access all of the other slides and videos and stuff okay?
Yes.
Yeah.
Right on. Sky is finally blue here again. I don't know about for where all of you are, but it's better. But apparently the East Coast is getting all of our smoke now, so. Guess we're all tired, huh? Apologize again if my lungs make terrible noises during this lecture. I'm still feeling pretty bad, even though the air quality is getting better. So once again, if I start coughing a whole lot, I will mute myself so you don't have to hear that. But hopefully it won't get to that point today. Things were better outside than Monday, so as I say, I have to cough. But anyway, it's 2, so let's actually get started. This is our last lecture before the first test. So the first test is going to be on Monday. And as I said a couple times, the way that's going to work is the test will be on Canvas. You probably noticed I put up a bunch of sort of headers for the different tests on Canvas, just saying when they are. But there'll be a link to the actual test on Monday. And the way it's going to work is it'll be entirely on Canvas, but you will need to use Lockdown Browser for it. So if you haven't used that before, I definitely recommend downloading it early and getting familiar with how it works. But when it does come time to do the test, what'll happen is you should navigate to it through your regular browser, and then it will launch Lockdown Browser. But again, if you do have to have it downloaded already, so make sure you've done that before Monday, so you're not using time for that. But the way things are going to work on Monday is we're actually going to spend the first like 20-25 minutes in this Zoom room just talking about last second review stuff. So that'll be your time to get answers on anything you're still not sure about, anything you want to talk about at the last minute. And actually after today, I'm also going to post a link on Canvas where if there's something you want to make sure I go over again on Monday before the test, you can just tell me what it is in a little submission box. And that's totally optional, but if you put things in there, that will be helpful. But yeah, so we'll talk about review stuff for 20-25 minutes, and then we'll stop the Zoom session at about 2:25, and then the test will open right at 2:30, and you'll have until 3:15. So it'll be 45 minutes, 30 multiple choice questions. There will be a couple of little extra credit questions on there, but it's just 30 multiple choice questions. They'll be similar to the kinds of things you've had on the quick quizzes. And so because it's on Canvas, it will mostly auto grade you, but I will have to go through and put in the extra credit questions manually. So it won't, when it grades you after you finish the test, it won't count the extra credit, and I have to go through and do that later. But again, the tests are not something you can do late. If you miss it, you miss it. I mean, you can open it late, but it won't be available after 3:15 on Monday. But also remember that, I mean, you should all take the test, but if something happens that you really can't, there'll be 4 tests this semester, and the lowest one drops, no questions asked. So there's that option if something goes really wrong. But I do recommend, being at your computer. The computer's definitely better than mobile if you can, making sure it's plugged in and charged, making sure your internet is stable, and making sure you're comfortable. And I will also send another email with these details probably on Sunday afternoon, just to remind you of that. But yeah, that's what we're up for. And then on next Wednesday, we'll start talking about rocks, and igneous rocks in particular. So there is going to be one more quick quiz. I know it initially sounds kind of terrible to have a quick quiz due the day of the test, but it's one of those things, like it's one question, and it's something that I think will help you understand. It's a topic I want to make sure you have down before the test. So by doing that, you'll at least have looked at it. And so you can open the quick quizzes back up, I believe, and look at them. And all of the answers have explanations. So if you're not sure how something was, you can go back and look at those to study. All the slides will be online. This lecture will be online after class today. All the videos are up. And definitely make use of those bullet points and study guides. So there's some stuff in the chapters in the book that won't be on the test, but everything that's on those bullet points is stuff that is fair game to be on the test. So when in doubt to structure your studying, look at those. But for the actual test, it's closed everything. It's a test. So any questions about any of that?
Sir, for a recap, when is the test?
So the test, the recap will start at 2, and the test will be starting at 2:30.
No, when is on what day is the test?
Monday, this coming Monday.
Okay.
So the class schedule is on the syllabus and on Canvas. So if you're ever not sure about when something is happening, you can look on there.
Thank you, sir.
Anything else before we finish our last mineral stuff? Where do we download Lockdown Browser? So you can download that, I think, from Canvas. But I'll send some instructions on how to do that later as well. So anything else? What is Lockdown Browser? It's Lockdown Browser it's a thing that basically doesn't allow you to open anything else on your computer, just the test. So it makes sure you're really only using your brain and the test questions. Make sense? Anything else?
What are going to be on the test?
So there's going to be 30 questions, like I just said a couple minutes ago, and anything that's on those bullet point study guide sheets is fair game. So it's not going to be everything that's in the book, but it is going to be anything that's on those sheets is fair game, and you will have 45 minutes to do those 30 questions. Anything else? And I will also, yeah, the link to the test, I guess I can put a link for Lockdown Browser on Canvas. I can do that. But the link for the actual test will go up on Monday. Anything else? Oh, the study guides are all linked on Canvas. They'll say bullet point stat/study guide for each topic. So if you're not looking at the Canvas page for this class regularly, you definitely should be, because like everything is there, including the test will be. All right, so what I'm gonna do now is I'm gonna get going on the actual lecture. And if you have any other questions, you can either put them in the chat box and I can answer them at the end, or you can just hang out at the end, or you can email me. But I want to make sure we have time to get through the rest of the mineral stuff. So as we started with last time, we were defining what a mineral is and talking a little bit about how they form. Again, our textbook definition of a mineral is that is a naturally occurring, so it forms in nature. If only people make it, it's not a mineral. It's solid, so if it's liquid or gas, it's not a mineral. It's crystalline, which means that it forms shapes that are, you have different faces connected at angles. So they're very geometrically shaped. They're formed by geological processes, which means that the Earth has to be able to form them on its own. If it's something that's only formed by biology, for example, it can't be a mineral. But there are some things that are formed biologically and geologically, and those are. And lastly, it has to have a definable chemical composition. So there has to be a chemical formula that describes that mineral, and that mineral is always that chemical formula. So those are the criteria. We talked about ways minerals form and ways minerals are destroyed last time. But today, we're gonna get into some more details. First, we're gonna talk about some ways to tell different minerals apart, because there are a lot of them. There are hundreds or thousands of minerals on Earth. Luckily, most of them are actually not relevant to rocks. So at the end of today, we're gonna talk about the main ones that are really relevant to rocks. But there are thousands of them, and sometimes you just need to tell them apart. And so first, we're gonna go through some ways to do that. What do you think what do you think are some ways that might be useful for telling different minerals apart?
If it's a solid
shape.
or not.
Yeah, I heard the color, the shape, the hardness. Yeah, all of those are the composition and the texture. Yeah, these are all spot on. Really awesome. Yeah, so I guess we'll go through. Those are basically exactly what I was looking for. So really awesome. Let's go through them a little more, because sometimes you need to actually use more than one of those to taste less sometimes. Don't make a habit of using taste, because sometimes some minerals are actually poisonous if you ingest them, but sometimes. But I'm gonna go through, like don't lick the asbestos. But asbestos is also really distinctive looking. I guess it's better to lick the asbestos than to like huff the asbestos, but I'm gonna go through the really basic ways that you all listed very well first. So color is a big one. Different minerals are different colors, but unfortunately sometimes color can also be tricky. So here we have a bunch of different colors. We have this white one, this yellow one, pink, purple, gray, green. These are all really distinctive looking, right? What if I told you all 6 of these are quartz? Because they are. So sometimes color can make the difference a lot. And actually, I mean, within like gemstones, these would be different things. This is, you would just call this quartz: rose quartz, amethyst, citrine, smoky quartz. I forget the name of the green one off the top of my head. So sometimes different gemstones are actually the same mineral. And so really all of these have the same chemical composition. But what differentiates a rose quartz from an amethyst is there's often other stuff like that gets stuck in the crystal, like impurities that get stuck in the crystal, just enough to tint the color. And that often has to do with where it forms. So sometimes color is a really distinctive thing. There are some minerals that really, like, nothing else is quite that color. But there's some where it's just a beginning place. But it is the first thing to look at. I mean, and there's some, like, if you see something that is like opaque blue, it's definitely not quartz. So it's still potentially useful. But on the other hand, like, you've got your pink rose quartz here, and there's another mineral that looks very much like this, that's pink, that has a similar crystal habit, but is called rhodochrosite and has a totally different formula from quartz. So you very often need to look at a lot more than just color. So does that make sense? I'm not going to ask you what the names of the different colors of quartz are. Don't worry about that. So another one is also kind of a color thing, and it's called the mineral's streak. And so many minerals, if you scratch them on something, will leave a mark. And often the color of that mark can really tell you what it is. And often the color of that mark is also not the color of the mineral. So like up here is an example of a streak test where you know, you're scratching these minerals on these, it's usually kind of a rough tile that it's like the official streak test stuff. But notice that this is pink and it leaves a white mark, and this is kind of gold colored and it leaves a gray mark. So often the streak can tell you something pretty different from the color of the mineral. So this is also rose quartz. So all quartz, like no matter what color it appears in your hand, is going to leave a white streak. And that this is galena. This is and it leaves a gray streak, even though it's gold looking. So it's sort of a way to tell things this color apart. But streak can also be useful for telling other really similar things apart, or for telling things that look, because some minerals sort of can they have obviously visible crystals, and some of them the crystals might be hidden. Or sometimes a mineral might have undergone a chemical reaction and look one color and actually be something else. So a place where streak is super useful is these examples on the bottom. So notice here, these two minerals look pretty different, right? This one's black and this one's red. And this one leaves a black streak and this one leaves a red streak. And so that kind of does what you think it would, but it can get complicated. So this one is magnetite and this one is hematite. They're very similar. They both have a lot of iron in them. But hematite is always going to leave a red streak. And actually the hema and hematite is from blood because it's red. Like there's not literally blood in it, but it's the same. They're like, oh, that's the color of blood, so we're going to call it blood rock. But sometimes hematite can be gray, and sometimes magnetite can be red, because they both have a lot of iron in them. And if that iron is exposed to too much oxygen, it'll rust and turn red. So sometimes streak is the differentiator. So here, you know, this rock here, or this chunk of mineral here, looks like this one, yeah? But notice what color its streak is. So in this case, even though these two rocks in this bottom example on the right look the same, like this one looks like this one, and this one looks more like this one, these two are actually both hematite. So this is more related to these red ones than it is to this other one that looks exactly like it. And sometimes streak is all you need to test that. So does that make sense? And as a side note, remember how we talked about graphite last time? Basically, when you are writing with a graphite pencil, you're taking graphite streak. That's what you're doing. So any questions on how that works? heard a microphone activate.
Can you hear me?
Yeah.
So you're talking about streak. Is that only when it's with like similar minerals, or can it be between like minerals that like don't have any correlation with each other?
Oh yeah, so you can use this to test any mineral. Most minerals have a streak. It's sometimes the most useful when things look really similar and none of the other tests are very helpful for telling them apart. But yeah, you could take a streak from, like here, this galena and this quartz are not even kind of related at all. But they're still doing a streak test. It's just, usually for for some minerals, there's going to be a lot of things that make it easy to tell them apart, and sometimes it comes down to just one test. And so in this case, like, sometimes it's streak. Does that answer your question?
Yeah, so would this be like the last test you would perform if it's not really relevant?
I mean, it would depend on, sometimes you might not need to do it. And sometimes it kind of depends on what you're looking for. Like if you had a chunk of rock that looked like this, you might want to do streak first because it would tell you if it was magnetite or hematite. So it's just sort of, depends on what you're working with, really.
Okay, thank you. Yeah, that answered.
Anything else on this? I just put them in a totally arbitrary order in this slide presentation. You could look at them in any order. So another one is just looking at how shiny it is. So luster is, shininess or texture is another really good way to put that. So there are a lot of different kinds of shiny. And usually you can start to get a sense of what something is or isn't just based on what it looks like. So like if you find something that's dull and chalky looking like this, you know it's not going to be quartz because quartz is always shiny and glassy, for example. So the actual scientific term for shiny and glassy is vitreous. Dull is dull. A lot of geology words are actually really, really, really literal. Like if you look at these, like metallic, I mean, it looks like metal. It's metal, or at least has metal in it. So you can have metallic luster, you can have a pearly luster. So with something like this, if you were to sort of turn it in the light, it would reflect kind of like a pearl. How do you spell the word for shiny? It's on the slide, vitreous. And these slides, again, will go up after class today. No worries, it's okay. There's a lot to look at at once, especially with the chat window and the slide and me talking. But yeah, vitreous is glassy shiny. Metallic is metal shiny. Pearly is pearl shiny. Like they're really literal. So like a good example of something that's pearly is like if you've ever picked up a piece of mica, like, which is exactly what this is, or like I know that like a lot of paints or makeups have like a glittery shine in them that's actually mica, and it kind of reflects light depending on how you turn it. So that pearly is going to do something like that. Waxy, so this is a mineral. This is not a piece of wax, but it looks like a piece of wax. It looks, I guess there's no other word to describe that than waxy. And silky will often look like, you can see here, the silky one looks like it has these lines in it. See how there's these sort of horizontal lines across this? So a silky texture will often both look and feel either like it has lines or like it's woven. And all of this has to do with what elements are in it and how the chemical bonds are. But the silky one is really a tactile, like a touchable manifestation of kind of what the crystal structure is doing. But yeah, this is a thing you can look at. Like, let's say, like if you might find some very similarly colored, similarly shaped things, but if one is vitreous and one is pearly, you know they're not the same mineral. And even if we go back to this previous slide, whoops, that's not the previous slide. Like both of these are still kind of metallic. You can see they have that metallic sort of shine to them. But yeah, so sometimes this is a really useful thing. Sometimes it's not. Again, sometimes it's you only need one test to really tell two different minerals apart. And sometimes you need to do all of them. But does the luster stuff make sense? All right. Then the next thing, so we talked a little, this isn't the exact same slide from yesterday, but we talked about what crystals are. We talked about crystals as being geometrical shapes of flat faces connected at specific angles. And we talked, again, a little bit about this yesterday, or Monday. Today is Wednesday. We talked a little bit about this last time, about how every crystal has its specific, every mineral has its specific crystal shape that it makes, and it always makes that shape and not some other shape. So again, quartz is always going to be this hexagonal things with a pyramid on top. Feldspar is always going to be hexagons without a pyramid on top. So like with quartz and feldspar, you'd be able to tell them apart both because this doesn't have a pyramid on top and this does, but also this is a dull luster and this is a vitreous luster. These are garnets. Garnets always form this kind of dodecahedral, 12-sided D12 if you play D&D looking things. Ice crystals are always hexagons. But I don't know actually what you would exactly call the shape of a bismuth crystal, but it always does this. Halite always does cubes. And so basically you can have things that are similar in every other way, but if they're not the same shape, they're not the same mineral. But sometimes this can be tricky because sometimes the crystals are actually really too small to see. So if you remember, our definition of a mineral is that it has to form crystals, but sometimes it's hard to see them. Like if you were to look at a sheet of ice or, just a bunch of snow sitting on the ground, you wouldn't necessarily see that it's made of hexagonal crystals unless you got in really close with like a magnifying glass or a microscope or something. But it still counts as a mineral. If you can still find the crystals under a microscope, it's still a mineral. It's only if there's no crystals. So if we call this a hand specimen, like if it's big enough that you can see the crystals and hold them in your hand, this is a very classic example of a hand specimen. But if the crystals are too small to see, except under a microscope, you call it microcrystalline. So just little bitty crystals. Yeah, but just what shape is it is a really big distinctive thing. So does that make sense? And a lot of these are, I hope, pretty intuitive. It gets messier when you get into the microscopic stuff. But any questions on crystal habit? All right, so someone mentioned hardness before, and the hardness of a mineral is another really big thing, but hardness doesn't mean how resistant to breaking it is. Hardness means the relative ability of a mineral to scratch or be scratched. So whether or not it breaks is actually something else. But hardness has nothing to do with hitting it with a hammer and everything to do with like scratching it with a nail. And so there's a scale of 1 to 10. It's called the Mohs Mineral Hardness Scale. It's up here on the thing. Basically, it's a logarithmic scale. So basically, a 2 is 10 times harder than a 1. A 3 is 10 times harder than a 2, which is 10 times harder than a 1. And so diamond, which is the single hardest mineral, is the only thing that is a 10 on this scale, is like way the heck harder than corundum, which is a 9. So it's a really big difference. So rubies and sapphires, which are actually the same thing, just have different stuff in them and are different colors, are a 9. Quartz is down here at a 7. Apatite, which is kind of what your teeth are made of, is a 5. So your teeth are kind of hard, but not the hardest. And the softest is talc, to the point where you usually encounter talc as a powder rather than as a brick, because it crumbles so easily. And so the way to test this is just to scratch it. So you see this chart also has a couple of different things, like your fingernail has a hardness of 2.5. So if you were out there and you were like, I'm not sure if this is gypsum or calcite, because sometimes they can look pretty similar. If you scratch it and you can scratch it with your fingernail, it's gypsum. And if you can't, it's calcite. So like a copper penny can distinguish between calcite and fluorite. A steel knife can distinguish between some other things, or glass. So it's just, can you scratch it? And so that's why, like, as a side note, a lot of the most precision cutting tools are sort of diamond encrusted blades, because diamond is so hard that it can cut anything. But you can only cut diamond with other diamond, or I guess with lasers, but that's a little different. We're not going to talk about lasers in here. But does this make sense? So you might also notice is like a lot of these things that are a lot of really high quality gemstones, like a lot of precious stones that are considered particularly rare and special, are on the higher end of the hardness scale. And part of the reason that, part of the reason that's special is there are fewer things that are up there, because what's hard is really hard. But also they tend to be extra sort of beautiful and unscathed because nothing messes them up. Like plenty of things can grind up quartz, but not a lot of, pretty much nothing can grind up diamond. So any questions about hardness? So hardness isn't about breaking, but these next two, which are related concepts, are. So cleavage and fracture are two different ways that minerals can break. And usually a mineral will have either cleavage or fracture, will not have both. Can a diamond scratch a diamond? Yes. So things can scratch their own hardness level, but nothing other than a diamond can scratch a diamond. But you can pulverize a diamond, so that's sort of how they get the diamond dust on cutting tools. But yeah, that idea of pulverizing or breaking a rock ties into cleavage and fracture. So cleavage is basically, does the mineral split along a pre-existing plane of weakness? And so basically that sort of goes, okay, based on the chemical structure, based on how the elements, the atoms in this mineral are stuck together, there are going to be some places that are weaker and some places that are stronger. Because if you remember, we talked about 3 different kinds of chemical bonds the other day and how some of them are a lot stronger than others. Basically, if you have a bunch of weak bonds aligned in a certain way in a mineral, it's more likely to come apart at that plane. And we call that a cleavage plane. So like mica, for example, you can see here this person is just slipping a knife between layers of this mica. Basically, you have really strong bonds within each sheet of mica and weak bonds between the sheets. And so it's really easy to just separate the weak bonds between the sheets of mica. Exactly like, again, what we were talking about with graphite. There's weak bonds between the sheets of graphite, and that allows them to cleave as you write. And we'll talk actually a lot more about those sheets and what that means at the end of class today. But that's just like one example. Sometimes you can have things that break into chunks, like calcite here. You can see there's kind of some very, very straight lines broken through this chunk of mineral. And that's sort of where, that highlights where the weaker bonds are inside the chemical structure of calcite. And like, some of them are diagonals, like calcite and amphiboles, or diagonals, pyroxenes are vertical. I'm not going to ask you to know necessarily what has a vertical, what has a 60 degree, what has a whatever, but just know that cleavage is sort of where it separates along chemical planes of weakness, along places where the chemical bonds are weaker. So like things, and so in the case of, say, this pyroxene, at 90-degree angles are weak bonds. But if you were to go across it at a, say, a 45-degree angle, those are strong bonds. Does that make sense? So for minerals that have cleavage, if you whack them with something, they're probably going to break along the cleavage planes, because those are already weaker. It's way easier to break something that's weak than something that's strong. So like if you took a hammer to some of those, it would most likely just break following the cleavage planes in a very geometrical way. But there are some minerals that don't do that. And when something doesn't do that, you say that it just has fracture. And so things like garnet or things like quartz do not have cleavage. Even though they have very, very distinct crystal habit, they have fracture rather than cleavage. So if you were to whack a garnet with a hammer, you just get this smash pattern, right? You just get pulverized looking stuff. You don't have any nice, clean geometrical lines like you do sort of when you cut halite into cubes. I mean, that's why salt, if you look at it, is usually little cubes, because that's the cleavage of salt. But garnet, you just smash it. And so if you really just see something that just looks like a messy, broken mess, then you call that irregular fracture. If it has just no pattern to it whatsoever, it is irregular fracture. But sometimes, so you see like this is just a mess. But look at this quartz though. Do you see a pattern to what this break looks like? Like, do you see any shape? Yeah, circular, exactly. So do you all see these kind of circular, like kind of ripples in a pool looking thing? Now that I trace them with the mouse. So if you get a pattern like that, it's called conchoidal fracture. And so actually glass, which is not a mineral, has conchoidal fracture. But just something about the structure of quartz causes it to break in this very sort of smooth, glassy, circular way, as opposed to, say, garnet, which just smashes. And so cleavage is always going to be at a bunch of very clean angles. Irregular fracture is just going to be a mess. And conchoidal fracture is these usually concentric lines and sort of ripples. So does this all make sense? Does anyone understand, or does everyone, understand the difference between cleavage and fracture? It's also kind of a nice way if you're feeling a little stressed out and need to find out what a mineral is, you can just hit it with a hammer. Moving on, there's not really a good, pretty picture way to show this one. But basically, another one is called a mineral's specific gravity, which is basically just a way to describe its density. And so density, as we've talked about a lot in here, is kind of important in everything. It's important in plate tectonics because it determines what floats and what sinks. It's important in determining why the Earth is layered the way it is. It's also important in a lot of volcano processes and sedimentary processes and metamorphic processes. Density really is going to be an important concept that continues throughout this entire class. And so specific gravity is just a way to describe that, because sometimes you can't necessarily measure density without literally taking a sample of this thing. But what you can do is go, okay, this is this big, and I'm going to take an amount of water that's the same size and weigh them and just see what the ratio is. How much does 1 cubic inch of this mineral weigh versus 1 cubic inch of water? And so this is something that you would get as a ratio. And actually, this is used in, this is a measurement that is definitely not exclusive to geology. This is a measurement if you want to measure how much sugar is in something, you would take the ratio of the sugar liquid versus water. Or people use this for all kinds of other chemistry things, not just minerals. But yeah, it's just a ratio of something to one, or something, something, the weight of the mineral compared to the same volume of water. And so it's it's usually given either as a ratio or as a decimal point, so as a 1 point something. So either as a thing to thing, as a, I'll type it in the chat, water, so mineral. So it might be phrased like that, sort of one and then a colon in the other, or it might be a 1.00, something like that, where it's what happens when you actually divide the mineral density, the mineral's weight by the water's weight. So does that make sense? Because sometimes, if you remember, I mentioned rose quartz and rhodochrosite earlier. They're both pink, they're both have the same crystal habit, I think they both have a clear streak, but rhodochrosite is way, way more dense than rose quartz. And so this might be the test that you would use to tell them apart. Especially because, you know, I actually don't know what rhodochrosite's cleavage or fracture is, but this might be the one. So any questions about specific gravity? Then, and so those are all your basic tests, but there are some minerals that actually have some really special properties that make it, like if you see that, you know that's what it is. So like magnetite is called that for a reason. Magnetite is magnetic, you can stick iron to it. Calcite, if you put hydrochloric acid in it, it will fizz. And so also any rock that has calcite on it, you put hydrochloric acid on it and it fizzes. And yes, geologists make dropping acid jokes about this literally all the time. It's a very common joke, but this is often a really useful test. And especially because, and actually calcite is a pretty common mineral, but within a rock, it might look kind of like quartz. So this is a really useful test. If the rock fizzes, it's got calcite in it. Some things like we talked about, halite tastes salty. We talked about this last time, and here's photographic evidence of a geologist licking a rock. This is a thing that happens. Halite is just salt. It has a cubic cleavage, which is why you get little cubes of salt. So that's a thing you can do, but generally not recommended unless you're pretty sure you're looking for halite. Some of them, like ulexite, is sometimes called TV stone because it does this thing. Like it does a thing where if you put it down on something, it like magnifies it like this. It's pretty cool. I think if the labs for this class were in person, you'd probably get to play with ulexite. It's pretty cool. It does this. Our state mineral, benitoite, glows under black light, which is really cool. So I don't have this on this slide, benitoite. I'll type that in the chat if you want to look it up because it glows under black light. So yeah, sometimes, you know, sometimes you can only do, like if you pick up a rock and it does this, or a mineral and does this, it's ulexite and you don't have to do like any of the other tests. But usually, yeah, our state has actually a state mineral, a state gemstone. Actually, sorry, benitoite is our state gemstone. Yeah, we have a state rock, a state gemstone, and a state mineral. So our state mineral is gold, unsurprisingly. Our state gemstone is benitoite, and our state rock is serpentinite, which is a kind of metamorphic rock that's really cool that we'll talk about in a few weeks. California has so many official state things. But yeah, basically, if you want to know what a mineral is, just do some combination of these tests. Usually one of them is going to be kind of the smoking gun that solves the mystery. Any questions about this? So sometimes this is, so you might be wondering, like, why did we just do this? So sometimes this is useful because even though most rocks have only a very small subset of minerals in them, sometimes when you find an unusual one, or even a more common one, but especially an unusual one, that means that very certain conditions have to have been there in order for it to form that way. And so by identifying kind of an unusual mineral in a certain place, it can actually tell you a lot about what has to have happened to form things there, about the history of that place. And so that might not mean a whole lot yet, but I think it's going to mean a lot more to you by the end of this class, especially once we talk about the different kinds of rocks and learn about where these minerals come from within them. Yeah, but just being able to go, what is here, and think about why is that there, is a really important part of telling a story. But also, like, even if you come out of this class and like never want to analyze a landscape again, but are really interested in shiny rocks that look pretty on something, like on a jewelry or on display, a lot of times when you're trying to figure out a sample and like, is this a quality gemstone or whatever, a lot of the same stuff comes into play. So there are applications beyond geologic history, but we're going to be doing geologic history in here. Anything about identification before I move on? Because that was my last ID slide. Cool. It'll let me. Okay. Okay. So as I just said, so there are actually thousands of minerals. There are thousands of gemstones on Earth, but most of them are pretty uncommon. The ones that we really care about a lot in this class in general are what we call rock-forming minerals, are the ones that really make a major part of rocks. I mean, certainly you can, like, you're not gonna find a mineral just chilling nowhere near rocks. Like, they all form in rocks. But in terms of the major kinds of rocks that exist, really only a small handful of minerals are involved in the composition of the vast, vast majority of rocks. And so even though the tests that I just gave you for how to ID minerals can apply to literally anything, really in this class, there's a much, much smaller group of minerals that we're actually going to be talking about in here. But, you know, why is it that relatively few make up almost everything? What do you think? Like, just think about what's in the Earth.
Can you repeat the question, please?
Yeah, so why do you think that even though there's gajillions of possible kinds of minerals, most of what makes up rocks, most of what makes up most rocks are just actually a very small group of minerals? Yeah, most minerals aren't on the surface of the Earth. Actually, a lot of them, a surprising number of them are. It just depends on where you find them. But I mean, some of them you do have to dig for. But like in geology terms, like if it's in like a mine and you have to dig for it, it's still kind of the surface of the Earth because it's still the crust or the lithosphere. So like mines are still the surface, even though you're in a hole. But yeah, but you know, if you were mining for something, that means you have to be looking kind of hard for it. But like most rocks are full of just a couple of minerals. So the reason for that, any other guesses of they're resilient and durable enough. That's part of it. But if there were a lot of minerals that were forming, so I'll get to you in just a second. Yeah, if there are a lot of minerals that are forming and then getting destroyed, like a lot of more unusual ones, there would be geologic evidence of them getting destroyed. So yeah, they are more common. Maybe that's actually probably a better way for me to phrase this question. Why are some of them so much more common? What do you think? Olivine is definitely one of the really common ones. But why do you think some are just way more common than others? So easy to find, but what is kind of the same thing as common. So think about what is in the crust. So lightness is, I mean, lightness is some of it. Like the ones that you find on the surface are there because they're light enough to be on the surface. The stuff that's inside the Earth is denser and you're not going to find it. So they come in large groups. Yeah, you make a lot of them at once. But what do you need to make a whole lot of something at once? Like what do you need to make like a really, really big pot of chili, for example? Well, heat, okay. Yeah, you need the ingredients. Sorry, go ahead.
A big pot.
Yeah, so you need a big pot, but you need the ingredients. So Brianna's spot on with that. That's the reason there are relatively few minerals that make up the majority of rocks is that you have more of certain ingredients than you have of others. And so as it turns out, you have a lot of the ingredients to make a certain number of specific minerals and less of the ingredients to make the others. Does that make sense? Just like you're more likely to be able to like make a like chicken noodle soup or whatever than you are to be able to make like a fancy gourmet French meal based on the ingredients in your house or in your grocery store. That makes sense? So if you remember back in like the second day of class, I showed you this chart about the most common elements in the Earth's crust. And it turns out that just 4 elements make up almost everything. So iron, oxygen, silicon, and magnesium are by far the most common elements in the crust of the Earth. And you have a little bit of some of these others, but really these are the big four. And I would like you to remember these four because they're super relevant. But when you have so much iron and oxygen and silicon and magnesium and very little everything else, most of what kind of minerals and therefore rocks you're going to be able to get are going to have a lot of iron, oxygen, silicon, and or magnesium. And there's kind of only so many ways you can put all those things together. And certainly like some of these other elements will get involved. But really, like if you pick up a chunk of rock, if you just went outside and picked up a chunk of rock, the odds are most of its atoms are going to be these four things. So does that make sense? Like you can find packaged ramen at every grocery store. It's kind of like that deal. It is everywhere and anyone can make it. So I hope everyone ate lunch before class because I realize I'm using a lot of food metaphors. I'm sorry about that. But yeah, so these four things make up pretty much everything. And so in terms of the crust and really the whole earth, oh, you're hungry. Oh no. By the way, I don't care if you eat during my class. You're welcome to eat during my class. Just please don't be chewing while you're talking. That's my only request. Yeah, no, definitely it's okay to eat in this class. But yeah, I'm sorry I didn't think to say that on the first day. But yeah, yeah, Zoom class hacks. So anyway, yeah. If you can make food while still paying attention, that's also totally fine with me. But anyway, I'm gonna go on with this. You got your 4 ingredients, your very simple mineral ingredients that make up several major categories of minerals. And so there are these mineral classes. And I'm gonna throw a lot of words at you, but don't worry, really only 2 of these are gonna be very important. Remember how we talked about anions? We talked about ions the other day. And remember, an anion is a negatively charged thing. So most minerals are held together actually by these, there's a lot of ionic bonds involved where things will stick themselves together and then kind of pull in whatever else is electrically attracted to them. So we define mineral classes by what their anion is. So there's probably other ways you could do it, but just in pretty much all of these cases, the structure of any of these minerals will be like a bunch of that anion stuck together and then some other stuff. So when we talk about silicates, and all of these will be named for what's in them. So silicates are based around silicon. So you'll want to know the chemical symbols for these 4. So Mg, Si, O, and Fe. So that'll be helpful. But yeah, silicates have a bunch of these SiO4 anions. So this means 1 silicon, 4 oxygens, and the electric charge is -4. So this one is going to be able to pull in a lot of stuff. And so most of the minerals in the earth crust are actually silicates. You can have sulfides, which have metal, which you have a negatively charged sulfur thing is attracted to metal. So like pyrite or fool's gold is an example of one of those. So they're still, all of these are fairly common, but silicates are by far the most common. You can have a sulfate, which is metal and a sulfur and oxygen thing. And so gypsum, which doesn't look like metal at all, is actually still one of those. Gypsum looks kind of like a waxy, sort of crumbly, very soft thing. Doesn't look at all like metal, but there actually are metallic atoms in it. You can have an oxide where oxygen atoms bound to metal cations. So like both hematite and magnetite that I showed you earlier have a lot of oxygen and iron, which is why they kind of get magnetic and also rust. Halides, you have an anion from the second to right column of the periodic table. So it can be any of them, but in terms of table salt, it's sodium chloride, NaCl. It is salt. That's what that is. So your salt is a mineral, it's a halide. That's the one you can lick and it's okay. And they're all gonna taste salty, not just halite. Carbonates all have, so carbonates are one of the ones, are a major group, but they have carbon in them, as the name suggests. But we notice carbon isn't even on this chart. Carbon is super not on this chart. It's in this other less than 1%. But there's a lot of stuff that, you still get a lot of carbonates just because carbon is a biological byproduct. So there's carbon that is just around. And it sometimes gets incorporated into minerals. So I give this example of apatite, which is a mineral that you can find in nature, but it's also a mineral, it's also one that's very common in that biomineralization that we talked about. And it's actually, again, very closely related to the minerals in your teeth and bones. And then the last group is a native metal. It's just a big old chunk of metal. Just, that's what it is. Like the gold rush was finding native gold. Iron ore is native iron. Or iron in iron ore is native iron. And so that is all held together by metallic bonding, actually, rather than all these anions. So this might seem like a lot. There are a lot of groups, but don't stress. There are really two that are going to matter a lot in this class. So silicates are almost everything. We're actually going to spend the rest of today talking about silicates. And when we talk about igneous rocks, that's 100% silicates. And when we talk about sedimentary rocks, there are carbonates involved. So carbonates tend to form in sedimentary situations. But that's still like a mix of silicates and carbonates. And then your metamorphic rocks are just silicates and carbonates having stuff happen to them. So really, from the grand scheme of sort of figuring out geologic history and learning things about the Earth, it's really the silicates and the carbonates that make up the most of everything. And especially for this class, silicates are the one you should know really, really well. Like, you should be aware that these others exist, but I'm not going to ask you picky questions about them. But you are definitely going to want to know your silicates, because that's actually, if you don't know them well, it's going to make understanding, especially the igneous rock stuff, pretty hard. So any general questions about how this works?
Professor?
Yeah.
I have two questions.
Go for it.
First is that you will provide us the link on Canvas for the exam, right?
Yes, and I prefer that if you have any more test questions, you wait till the end.
Okay. Okay, sir. Okay.
Just I want to make sure we get through all of the material that's going to be on the test. But yeah, when I'm going to ask you minerals questions, but like in terms of specific mineral details, it's mostly going to be focused on silicates. But does anyone have any questions about these things, about mineral classes and cation or anions, before I go on and talk about silicates specifically? Okay, I'm going to talk about silicates. I think I said last time that there's not going to be any chemical formulas that you need to know, but I lied. I want you to know this one. This is the only one that I really want you to know this one off the top of your head, because this chemical formula is the building block of like almost all of the minerals that make up almost all of the rocks on the surface of the Earth. So all silicates have this same building block, and we call it the silicon-oxygen tetrahedron, or a silicate anion. So I'll type those things. So what that means is, so it's silicon and oxygen. So, or actually another word for this is just silica. So all three of those things, silicon-oxygen tetrahedron, silicon-oxygen anion, and silica mean the same, or silica anion, all mean the same thing. And they mean this thing where you have one silicon and 4 oxygens. And those things, the word tetrahedron comes from the fact that they form this little pyramid. And so basically you have in the middle this one silicon, and it has, and it is ionically bonded to these four oxygens. It is bonded. And so you have the silicon in the middle and then 3 oxygens at the bottom of the pyramid and 1 oxygen at the top. And so there are a couple of different ways that you can draw this thing. Like this thing on the left just shows where the electrons are. Actually, did I say ionic? Yes, it is ionic. It is ionic. I worried that I said covalent for a second, but it's ionic because this is an ion. So you can draw it like this. That really shows the all of the subatomic particles. All of the you do not need. I'm not going to ask you to draw. I'm not going to ask you to draw it. But you're gonna need to be very familiar with this pyramid structure because it makes a big difference in a lot of other stuff. So my guess is that you will be able to draw it by the end, just because you kind of need to know what it's shaped like. But no, I'm not going to ask you. I'm not going to ask you to draw atoms with particles and orbits ever. But yeah, sometimes you can represent this as a pyramid with the silicon in the middle and the oxygens, which are larger on the outside. Sometimes people just show the oxygens. But usually what you're going to see in most of the diagrams in our book and also in my slides are going to be this geometric sketch version, like on the right. And I do want you to know that it's a silicon in the middle with oxygens at all four corners. So that be familiar with that. But most of the way it's going to be drawn is this little pyramid. And so it doesn't actually draw the silicon, and it does kind of have the oxygens at the end. But the silicon is in there, just sort of know that it's in there. And so these little triangular building blocks are everything. Like the major rock forming minerals of the Earth's crust are all made up of different configurations of these things. Because this thing sticks together in a certain way, whoops, but it has a negative charge. It's an anion. It's an anion. So that means it's still going to get stuck to everything else. And so the way that it either sticks, and so it sometimes might stick to other silicas, or it might stick to stuff that's not silica. And so the way it sticks together and the other stuff that's involved leads to there being several different classes of silica minerals. And the way that those little pyramids stick together makes a huge difference for like everything. So does anyone have any questions about this structure or this chemical formula or what to call it? Also worth noting that today we're just going to go through these in the context of introducing them. But all of our igneous rock and volcano stuff, like everything about how volcanoes works, ultimately ties back to how these things stick together. So they're important. You're certainly not going to be drawing it on this test. But yeah. Ready to go on, or should I? We're good here. So silicates. There are a bunch of different kinds of them. There are a bunch of different categories of silicates that make up major rocks. And so I'm going to just go through them going from least to most complex. And so sometimes the chemical structure is just these tetrahedra are hanging out by themselves, and there are other metal atoms between them. And so we say this is an isolated tetrahedra one. Because they're just by themselves. None of them are attached to each other. And so in this case, this metal is usually an iron or a magnesium, because those are the other two, this kind of thing has the 4 most common elements in it. It's going to have either iron or magnesium, and then silicon and oxygen. And by introducing 2 of either iron or magnesium, it takes care of that negative charge, and everything just sticks together. And the best example of that is olivine, or peridot, if you're more familiar with the gemstone names for things. But this doesn't really show the crystal shape. The crystals of these actually also kind of look like little tetrahedra. And this is the most common mineral in the mantle, especially the upper mantle. But it is in some rocks on the surface. And so this forms at really high temperatures, because as it turns out, one of the things that affects how these tetrahedra stick together, how the building blocks can stack up, is how hot it is. And so if it's really hot, it's actually harder for these things to stick together. They're moving around more, and they're more likely to just float around separately than actually joining up. And also because they're just so individual, like this is not a chunky molecule. Like these are pretty sort of flat molecules. And so it's actually very easy for them to pile up in a lot of layers. And so these isolated tetrahedral silicates are usually pretty dense and pretty metallic and form in hot temperatures. So does that make sense? And as we go from the least to the most complex silicates, it also means that the least complex ones have smaller molecules, and the most complex ones have bigger molecules. The least complex ones have simpler structures. The most complex ones are chunky. The least complex ones form at hot temperatures because it's harder for things to stick together. The most complex ones form at lower temperatures because that's what allows more silica to stick together in more weird ways. And also, the least complex ones are more dense because if you can just pile a lot of it up, it's more dense. Whereas the most complex ones are the least dense because there's more space between all of the tetrahedra. So it's always this spectrum of just, all of those things are correlated to each other with silicates. And so as we'll talk about a lot more with igneous rocks, you're never gonna isolate the least complex ones and the most complex ones in the same place unless something weird has happened, because they can't form in the same place. But those are your isolated ones. Any questions about, and you don't need to know this formula. So I'm gonna put chemical formulas on these slides, and certainly looking at them can help you understand what's going on. Like in this one, you've got your silica, but everything else is metal. So that tells you that. It can be useful, but I'm never gonna ask you to memorize a chemical formula other than that SiO4. So are we good on this one? And also don't worry too much. We will go through these again in the next unit because it matters. You will see all of these again. So moving up in complexity then, sometimes you get what's called a single chain silicate. So in this case, all of your little tetrahedra, all of your little silicas will join at one corner. And so you'll get just like a string of them. You'll get multiple strings that are held together in the middle, sort of magnetically, usually by metal, but sometimes by sodium or calcium. See, these can get to be pretty complicated chemical formulas. But basically, it's mostly a case of your silicas and then something metallic or close to metallic in the middle, holding them together. And so these are bigger molecules. Like these are all really little molecules, and this is already bigger because there's more stuff stuck together. And also in this case, there's kind of one metal for every there's like one or two metals for every one silica. And in this case, there's more silica per metal, just because more of them are stuck together. More of this rock is just made of silicon and oxygen than the previous one. And so what those looks like, that group of rocks is called pyroxenes. And part of that, the pyro in the name is because they still form in very hot temperatures. They're still pretty dense because even though these are stuck together, they're still just little chains. So it's still pretty easy to stack them up and make quite a dense rock. So there's also a lot of this in the mantle, but this does exist in the crust. These are pretty hefty. Like the specific gravity of one of these guys is they're heavy. Does that make sense? So then moving up in complexity, and actually I will tell you now, for the test, I'm not gonna ask you a whole lot of details on these individual kinds yet, but I will on the igneous rocks and volcanoes one because it controls everything. So this is a little bit for this first test, but it'll be a lot on the second test. moving up. So then you can get what's called a double chain silicate. So here you still have these chains like in the pyroxenes where they're stuck together at the corners. But now here, the chains are also stuck to each other. So you have some silicas that are stuck to 3 other silicas instead of just 2. And in this case, like, it's still a flat molecule, but now there's even more silica. And it actually doesn't require metal to hold it together. The silica sticks to itself all over the place. But if you notice, there's these kind of big hexagonal, hexagonal spaces in the middle now. Yes, we absolutely will go over these again. But there's these big spaces in the middle. And so that's where like other atoms can just go in these spaces and hang out. And so this group of minerals is called amphiboles. And you can see this has a really gnarly looking chemical formula. And do not worry about this chemical formula. But what this should tell you is that like a lot of stuff can go in these spaces. So even though the silica is stuck to itself, any one of these, sodium or calcium or magnesium or iron or aluminum or whatever the heck, can go in these spaces and hang out and kind of fit into that mineral structure. And that's why you can get different kinds of amphiboles. Just like there's different kinds of amphiboles, there's different kinds of pyroxenes. Olivine is just olivine. So actually, as you get more complex, there's also more possible versions of that kind of mineral. But see, these, they're starting to, this is less dense now because, things are still, you've got a space in here, but there's something in it. Everything's in all the space here. But now you're starting to get bigger spaces that might actually still have pretty small atoms in them. So this is starting to get less dense. Basically, the more space you have, the less dense it is. Does that make sense? And so these guys are, you see more of these in rocks on the surface. Like these, you don't find them so much in the mantle, but you do find them a lot in the crust, just because of their density and because of their composition, and also because of the temperatures in the crust. These form under slightly cooler conditions because they need to in order to stick together like this. Any questions on that one? We'll talk even more about what the physics of this means later, but later after the test. Moving on up, so sheet silicates I've actually talked about a lot, because remember how we talked about graphite and we talked about mica. We talked about things that form layers and that have strong bonds within the layers and weak bonds between the layers. When I'm talking about that, I'm talking about sheet silicates. And so mica, again, is an example of that. So here, this is a little bit of amphibole in it, but all of this stuff is mica, which has this really nice hexagonal crystal habit that you can see kind of corresponds with the hexagonal shape of the structure. And so with these now, rather than just forming chains, like you can see there's some similar shapes to what's going on over here. But now rather than forming chains, you get kind of all of these silicas are attached to 3 other silicas instead of 2. Everything sticks to itself. And so these are all really strong bonds between the silicas. But you have a lot more sort of big spaces between them. And again, these chemical formulas are wacky. There are just so many different things that can fit in these spaces and also fit in the spaces between the layers. Because the way these things want to form is they just form a sheet, and then something else actually holds the sheets together. So for every layer on this piece of mica, and I hope you can see there's a lot of layers on this thing, every layer within itself is very strong, is held together by very strong chemical bonds that look like this, that silica stuck to silica stuck to silica. But between every layer is going to be a bunch of other atoms. And so that's why these are so, like if you just were to try to break a mica just this way, it's pretty hard to do. But if you were to, but you can peel off the layers very easily, just based on this sheet structure. So does that make sense? So these are also not very dense at all, partly because you have big spaces between everything. And also partly because the space between the layers, even though there's some atoms in it, is still a space. So these are not very dense. You do not find these in the mantle. You pretty much only find these in the crust, and they form in relatively cool conditions. I mean, relatively cool conditions for molten rock. All of these still form in molten rock. You have to have like liquid stuff before this to form. So even when I say like cool temperatures, I'm talking like slightly less hot lava. You can have very hot lava and not very hot lava, but we'll talk more about that later. But basically these you only get in the crust at the surface. We good on that? I know there's a lot of words and a lot of definitions and a lot of chemicals this time. This will, again, come back. And so then there's actually just one more kind of these. And the last kind is the most complex, and it's called a framework silicate. And so in this case, they actually just even gave up on drawing the little oxygens at the corners because everything is stuck to everything else. These things form like a three-dimensional shape. They don't just form flat layers or chains or individual things floating around. They form very complex geometrical shapes that have a lot of space in them. And so like you have silica stuck to silica stuck to silica in a number of different patterns. But some of them might have different stuff in the middle or different stuff in all of these spaces. But you can also see that there's just the big space. Like there's a lot of space in there compared to this or this. And so this is by far the least dense. You're only going to find these on continents even. Like you don't even get these in ocean plates because they're so fluffy as far as minerals are concerned. And so quartz is an example of one of these. Feldspar is an example of one of these. And so those are the two single most common minerals in the Earth's crust. And they form in pretty cold for lava conditions. They're very common and they're very light. They're not very dense. And yeah, so you can see that something like this big spiky ball, very, very different looking molecule from just this sort of alternating pattern of things. But they all have the same building blocks. They all have these same tetrahedra that lead to fundamentally different looking, but also fundamentally different acting minerals. And so the way that these minerals act because of their chemical structure, as I said, is especially relevant for volcanoes. And that's why I'm kind of ending our minerals talk with this. And we're going to start our igneous rocks and volcanoes talk by coming back to it. So in terms of what I want you to know about these guys for Monday's test, sort of know the difference, like know which ones are like more dense and less dense, like know what the difference between a framework versus an isolated tetrahedron is. But I'm not going to ask you like what kind of mineral is this yet. Just sort of know frameworks have a lot of space. They're stuck together a lot. They're not dense. Versus isolated tetrahedra are very dense. And sort of be familiar with that sequence. But actually that's it for today. So does anyone, and that's sort of the cutoff for what's going to be on the test. So does anyone have any questions about the content of the lecture today?
Can you go over cleavage and fracture one more time, please?
Yeah, so yeah. Cleavage is when a mineral breaks along weak planes that are where the weak chemical bonds are. So like, again, our mica here, our sheet silicate, the bonds within each sheet are strong, but the bonds between the sheets are weak. And so it's going to break there. And so something that has cleavage follows weak bonds and breaks in very geometrical patterns. Whereas something that has fracture just either kind of smashes irregularly or forms these sort of glassy, ringy patterns and doesn't break in any sort of geometrical way. Yeah, well, hold on. Does that answer your question?
Yes, thank you.
And there's also more description of this in your book. So like definitely look at your book when you're studying. But yes, I'm going to upload the slides immediately after this, and I'm going to upload the video as soon as it uploads, given that my internet connection is really slow. I will link the download for the Lockdown browser after class as well. And there will be another quick quiz that goes up right after class, but it's literally one question. Any other? Okay, it's actually 3:15. But does anyone? So if you're done, feel free to go. I know Arnav had another question. If anyone has any more questions about anything, feel free to stick around and ask. And
Thank you.
and I'll also put up that request for going over things box for Monday.
Thank you, Professor.
Professor?
Yeah.
Professor,
Yes.
I have a question like, the exam would be online
Yes.
on Canvas. The link would be on Canvas.
Yes. I'm going to put the link on Canvas. It'll be up on Monday, but you won't actually be able to start taking it.
And I guess, okay.
And I will send another
Okay.
email.
And
I will send an email on Sunday reminding everyone of how this is going to work.
I guess, okay, thank you. Included in that.
And if you think of anything else, feel free to email me too.
So how many topics are there?
So anything that I put on those little study guide pages on Canvas is something that could be on the test.
Okay, thank you.
Um,
Thank you. Have a nice day.
you too. What's up? Yeah, go for it.
I just want to ask, do I need to make up my missing word?
So I sent an email about that. So I set it to be for right before when the test starts. And I know that seems like it's a short amount of time, but most of the assignments are like 1 minute long. Like they're designed to be 1 minute. So I put it then so you will have made sure to have gone over everything and have like looked at it before the test, just so you're in the best possible shape. But everything that says quick quiz will take you like 1 or 2 minutes by design, and the vocabulary things are pretty short. Do you have the book?
Not yet.
Okay. So I would recommend connecting to either the library and seeing if they have an online copy, or actually buying it as an ebook. So I can send you a link after class of where you can get the ebook, because then you'll get that the fastest.
Okay, thank you.
And did you notice there's also a link up there that has all of the videos of the past lectures, so you can watch those too.
What about the study guide for the quiz or test?
Those are also on Canvas. So everything is on Canvas.
Okay, thank you very much.
And feel free to send me more questions if you have them.
Have a nice day.
You too. Thanks. So Eli and Ethan, are you hanging out to ask questions, or are you just, okay, that answers that.